Okay, so welcome to our first little introductory lecture here in Cal 1. My name is Mark Corbet. I'm your instructor for the semester. So let's just get at it. The first part of this course is going to be entirely taken up with the concept of the derivative. And so we're going to talk about that. And the main part of that is actually going to be what's called the tangent line problem. So remember, when I'm doing this, I am assuming that all of you have a good grounding in pre-calculus, which means you know how to deal with a little bit of extreme values, undefined values, and also that you all have really good skills in trig. So if you do find something that you're a little behind on or weak on, look it up in the book or look it up somewhere else and make sure you make that up. So we're going to go ahead here and move this cursor down. It's always fun to do that. So we're going to do the tangent line problem here. Go down a couple pages and give me some space to work. Here we go. So what we're going to talk about here is just a typical kind of problem that we have in any kind of analysis of a function. Oh, try to do that a little straighter. There we go. So this is our x-axis, this is our y-axis. Notice when we're graphing at this level, we do want to have our analysis pretty good. So we will always include a little arrow on the x-axis and label it, an arrow on the y-axis and label that. Failing to do so is just lacking in just basic accuracy and is going to cost you points, by the way. So we'll keep that in mind. So here's a function, and here's just kind of a typical function here. It's not a straight line. It's just a function that goes up and down. And we can see that the function kind of, in this case, seems to increase as we go left to right. And that would usually be graphed by or accounted for by doing some kind of countability. My habit is going to be always to put my tables for things underneath a graph like this because that really gives you a better accounting for what's going on with that graph. So we will tend to do that, make that actually a little smaller now so we can see what's going on. Another thing about this we can do is we're going to be doing a lot of stuff under that, so it's going to be important that we might actually, under the x and y, start including other information. So for example, it looks like on the entire domain here, or at least this part here, let's say from x is equal to 0, and we'll call this value over here. We'll name some values here. We'll call this value A and this value B here on my graph, and we'll put these values into a table to kind of account for it. So that's kind of split up my table already. I've got a good, although it's messy, admittedly, I've got a good account of what's going on here. So, and it's directly below, so I don't have to label as much here when I'm talking about a value. So for example, when I look at this point right here, that's actually the value that we use the function. So if I do y is equal to f of x, don't know what it is, this would simply be f of a, and this value over here would be f of b, and this value here is f of 0. So we can talk about those values, and certainly down on the bottom, from what it looks like with this graph, I can see this graph seems to be increasing. So on this whole area here, I might use an arrow and do that sort of thing. Actually, you guys are probably used to it, less using a little arrow like that for each one. So when we say a graph is increasing, we're going to use a little arrow like that. When we're saying it's decreasing, we're going to use an arrow like that, right? So that's increasing and decreasing, just to get a little idea. Sorry for the slobbiness. So that's basically what we've got. So, and sometimes, like I said, down here, we can just be succinct and do that for the entire place, let's say from 0 on. we just use that increasing here. Notice we can also see from what appears on our graph that this graph seems to be concave up. And we'll talk about that later on a little bit more. So we're going to use a symbol that looks like this for concavity, concave up, and concave down. And I'm just kind of looking at the behavior generally of what this graph is doing. So I may include that down here. Say, you know, it looks generally on this interval, this graph is concave up. And we can see, certainly, we can start listing that on the intervals. For example, this interval here, we might actually list specifically as the interval from A to B. So we might actually break that down here, and that is the interval from A to B. And we can do that in different ways, but the easiest way we could do it is simply use notation, and I'll use open notation. So from the value A to B as an interval, this function is increasing. And we can actually do it here and say, hey, on the interval from A to B, the function is increasing. Notice it's an open interval, so I'm not including A and B because, you know, I mean, I could have, because this graph is obviously from the visual increasing from A to B inclusive. So we're just guessing. So this one I could have been the inclusive A to B, which would be the hard brackets. So that's going to be the kind of notation we use. We could have used less than or equal to X less than or equal to B like this for this bit here, and this one here we could have used A as less than X is less than B. So we could have used either one. Just kind of reviewing and taking a look at that. So we've got this graph here, and you know, with this graph here, I'm going to work on that. So let's actually redraw this a little differently here. I'm going to redraw this graph over here. Oh, I did that again. Look at that. Wow, there we go. Kind of straight. Now we're going to look at the A to B once again. We'll have the X and the Y. We'll work that out. And this is f of A, f of B. Being a little less here, these values. And I have that graph again. So let's take a look at this graph here a little more. So what I'm going to do this time is I'm actually going to draw a line between these values. So we're going to go over here. Sorry, we're going to get that picture of this graph. So I don't know why my graph isn't showing up here. Sorry. There we go. We're going to try to keep that menu here. The ribbon. There we go. So we've got our ribbon here. So we go back down here. Here's our graph. I'm going to look at my insert, my drawing. There we go. I want to change my pen color to this blue color here, and that's what I want to do. So now I'm going to draw the line going through these 2 points. I do apologize for the wonderful straightness of this. So this is the line going through those 2 points. It is horrible, so we'll give that a shot again. Let's draw, there we go. That's a better line going through the points like that. There we go. So that's the line going through those points, and we know the line should have AX plus BY equals C format, or Y equals MX plus B format. That's the format of this straight line, and it's clearly going to be delineated by the slope and the intercept. Well, the intercept is obviously over here, but the value of that line, or the slope, is pretty easy to do. It's going to be M, and it's going to be, you can do it a number of ways, y2 minus y1 over x2 minus x1. There's our standard way of slope. And we can kind of now label these points now. Well, this must be, well, we'll call this one x1, and we'll call this one x2. And therefore, this value here will be y1, and this value over here is y2. So that means that x1 is actually going to be A, and x2 is B, and y1 is going to be f of B minus f of A. So this is going to give us our slope is really based on these values here as points. In other words, our x1, y1 is actually the point A, f of A. That's what I use there. And my x2, y2, that's going to be expressed by B and f of B. So put that in point notation. So that's how I get this. This line we're going to call the secant line. Secant line. So the slope we just did, that's the slope of the secant line. So we've done the slope of the secant line, and we can do that. And we can discuss it quite easily. And I can do an example of that real quick. I can do something like y equals x squared. We'll do a real world example with that. Y equals x squared. This is a really simple, whoops, my apologies. Oh, sorry, my pen's sticky. There we go. Try not to get our pen to be all sticky again. So x and y, I can do 1 and 2 here. And x squared is really easy. So x squared will look like that. This value here is 1. This value here is 4. So the secant line that goes through here, for example, we can express that very rapidly as well. We have 1 point is 1, 1. That's my first point. 2, 4 is my second point. So the slope of the secant line going through, in particular, these 2 points would be y2 minus y1, x2 minus x1. 4 minus 1 would be 3 over 1, or 3. So this would be the expression of the slope in between 1 and 2. So we have an expression of that slope. And notice the slope is positive. So we can do a couple of things in our analysis. So I can do my little table analysis, which is always helpful. So I got 1, 1 here, 2, 2 squared is 4. We said that already. And I said the slope was positive 3. So that's kind of the, if you want, the average slope between these two. And the slope being positive, so m is positive here, tells me that this function is increasing because between 1 and 4, on average, it's increasing with a slope of 3. And in fact, I can compare that slope to, let's say, if I decided to do the same thing at the value 4, if I did that, I'd have 16. And if I did that same thing with the slope of the secant line at that point, that would be 16 minus 4. Whoops. Yes. And then 4 minus 2. Just making sure here, I'm looking. 16 minus 4 would be 12 over 2, which would be 4. So the slope here would be, 4, please. 6. Thank you. Those people in the audience screaming out that was 6. It is 6 indeed. So the slope here is still positive, but it's a bigger slope. So it's still increasing, but it's kind of increasing more, which makes sense because this is a quadratic. So if I actually was to look at this graph and do a little extension of it up here, we would see at 4, the secant line would have this slope. So the slope is 6 here, and the slope is 3 there. And as I go down, obviously the slope between 0 and 1 would be 1, so the slope there would be 1. And as I go backwards here, because this quadratic keeps going down, I might actually get a negative slope if I did a secant line here. So what this kind of tells us with the secant line is the secant line is kind of a way, if you go way back to the original problem, of describing what is going on with this function. Secant line between 2 points kind of gives us an indication that the line is either increasing, decreasing, or doing something else. Now that's a limited thing because, you know, our graph could be doing something between 2 points that we choose with a secant line. So for example, if I've got a graph that does a Humpty Dumpty thing up and down, and I choose a secant point here, once again, sticky pen, sorry, gonna have to cure my pen of that. There we go. If I choose a secant line here and a secant line here, or a point, and I do a secant line like this is probably an inappropriate choice because there's all kinds of things. In fact, this might be generally describing the slope of the secant line here being positive, but it certainly doesn't describe what's happening with the graph over here where the slope is negative. So I have to be pretty choice about the choices I make for my secant line. In general, when I choose my secant line between two values, 2 points, the points need to be very close together. In fact, if I get a really complicated moving function, maybe something like that, but I'm very circumspect and I choose a secant set of points that are really close together, well, what do you know? I get a fairly decent description of what's going on with the function, at least at this place, because the two values for these secant, for the secant line going through those points are really close together. So here's the tangent line question. The tangent line question is, well, what we have here is we have that big picture of the graph maybe doing this, right? And I'm just going to arbitrarily, and I do mean arbitrarily, shove this in the Cartesian plane. So I'm going to put a point of reference, but it could be anywhere here, right? Behaving in any way. So we saw before that if we took 2 points, and I'm going to do them in red, here and let's say here, that this secant line does a fair to middling job of describing the behavior, but it's limited. So instead, what we're going to do, I'm going to do this in pink, is, or maybe some other color here, yellow here. So what we're going to do is I'm going to choose this point, and instead of choosing a secant line, I'm going to draw a tangent line. And that's my best line, and I do mean my best line, which is limited, that actually only touches the curve at one point. And this is called the tangent line. Now the tangent line only touches at one place, and that means you're kind of balancing it. That tangent line, notice, is at a specific value. We'll call that x for now, the tangent line at x. So if I can find the slope of the tangent line at the value x, now I'm really cooking with gas because that line is going to describe exactly what's going on at that point. So how am I going to do this? Well, eventually what I'm going to do is I'm going to take advantage of the secant description, but do that with the tangent line. So here's what I need to do. What I need to do is I need to grab that tangent line, and I really going to draw that in a different way. I'll go backwards here a little bit. What I'm going to do is I'm going to go back and draw that tangent line. Actually, I'm going to actually draw my secant line a little better. Pathetic drawer that I am. Hard to get a ruler to go here on the computer screen, but that, oops, that's not quite right. There we go. There's my better line. So there's my secant line. And for the tangent line, what I'm going to do, let's do it in green just to be different. I'm going to start here, and I'm going to draw my line again, almost of it's going here. but this is going to be my point x, and this over here is going to be some distance from x. So some delta x. So we're going to say x plus delta x. So what I'm going to do is now I'm going to define this slope is going to be, well, the first point is going to be here, so that's x f of x, and the second point here is going to be f of x plus delta x. So when I talk about the slope of my tangent line, I'm going to define it kind of like it's a secant line, so I'm going to do my y2 minus my y1 over my x2 minus my x1. And when I work that out, what I actually get, if I draw a little more carefully and write it carefully, f of x plus delta x minus f of x all over delta x. Well, that's not all that helpful, but here's the trick. I'm going to decide to make this delta x smaller. So I'm going to redraw this in a slightly different color, and I'm going to put this delta x smaller. So I'm going to put it here, and then I'm going to put it here, and then ultimately I'm going to put my delta x really small, so what I'm actually drawing is a tangent line, not a secant line. So this is how I'm going to turn my slope of the secant line into this tangent line, and what I'm doing is I'm making this delta x smaller and smaller and smaller, so ultimately x is here and my x plus delta x is right beside it. So this delta x is going to become very small. It's going to go to 0, and the delta x here is going to be very small, and it's going to go to 0. This is something we're going to call a limit. So before we do the next step of this, we're going to do the limit process, but that's going to be the next little bit. But I want you to think of why we're doing this is we're doing calculus now, because if we do make that delta x smaller, what we're going to do is going to be talking about the slope of the tangent line, and that's what we're going after. What the advantage is by doing the limit is that's exactly what we do, and we describe it in this really theoretical way, but what we're ultimately going to get is if we start with y is equal to x squared, we're going to get the equation y is equal to 2x, and this is always going to describe the slope of that. The result, y equals 2x, we're going to end up calling that the slope of the tangent line all the time. We have a word for that. That's going to be the derivative of f of x, or f prime of x, which we're going to write it this way. And that is really the whole course. We can go home now, right? Or you guys are already home anyways. But that's it. That's really what we're going after. Now, it's a shortcut here, but when we actually do it in the long way, that's what we're going to be going after. But the first thing we ought to do is start working on limits. So you need to open up your textbooks, get to chapter 1.2, read a little bit of 1.1. It's pretty well what we just did, and start working and go and pick up the video on 2.1. I'm going to do an exercise on limits that you guys can start with.